In this lecture, we're going to be looking at how we describe the velocity of plane waves, looking at how wave fronts propagate, and how quickly they propagate, how that's related to material properties and other things that could be going on in the processes of Maxwell's equations. There are a couple of concepts that we want to be able to take away from this. The first and most important is understanding the concept of phase velocity. So you need to understand the definition of phase velocity, and you need to be able to apply the formula given that you know how the frequency omega and the wave number beta are related to each other. We're going to introduce the concept of index of refraction. In microwaves and RF, we tend to describe materials by their dielectric constant and their permeability. In optics, which is just another branch of electromagnetics that many of you may find yourself working in, tend to use the term index of refraction. So you want to be able to analyze the index of refraction and understand or comprehend where the index comes from. And finally, the thing that we're going to do is we're going to try to familiarize you with the concepts of group velocity and dispersion. These are more advanced topics, so you need to know what dispersion is and understand what its effects are on signals. We'll give you some examples today. We'll talk about more examples later on in the semester. And you also should understand the macroscopic effects of dispersion in wave propagation systems. So the first and most important thing that we're going to be talking about in this lecture is the phase velocity. And for phase velocity, that means we're talking about waves at a single frequency. And it gives the speed at which the wave moves through the medium that it's propagating in. We know that in the time domain that the electric field is given as a vector, which gives the polarization. In this case, this vector would be in the xy plane. It could be x polarized, y polarized, or some combination. And then cosine omega t minus beta z. And we know that this is propagating in the plus z direction because of what we've seen in the previous lectures. So time equals 0. The wave is cosinusoidal in space. We see that it has its peak here at the origin, and then it oscillates a wavelength. It moves along, but as time progresses, those peaks move to the right. Okay. So at time equals 0, I have this peak indicated by this red arrow. But at some later time, t0, that peak has moved to the right by a distance. The distance that it's moved is omega t0 over beta. Okay. That's the shift that the phase has made over that time. And we can define the phase velocity as that distance divided by the time, and we get omega divided by beta. Okay. For lossless or low-loss dielectrics, that phase velocity is given as 1 over the square root of mu epsilon, because we know that beta equals omega square root mu epsilon. A concept that I want you to be exposed to, we're going to see this come in a little bit later on in the waveguiding section, is that phase velocity can be slower than the speed of light, which you're probably quite comfortable with, but phase velocity can actually be faster than the speed of light, and that doesn't violate relativity. We will see phase velocities faster than c for rectangular and circular waveguides in the next section of the course, and we'll talk a little bit about what that means when we talk about group velocity. Index of refraction is the terminology that's used to describe dielectrics when you're dealing with optical wave propagation. And there's some fundamental differences between optics and RF, and I'm not going to go into them in this lecture. But we tend to describe materials by their index, n, and we're kind of sloppy. We'll use n interchangeably to mean the index of refraction or the real part of the index of refraction. And normally when you're talking about a good optical material, a glass, something that you make a lens out of, fiber optic, the real part dominates the imaginary part, just as we saw in real and imaginary parts for the propagation constant in the previous section. And so n and kappa are very closely related to alpha and beta in the lecture that we gave previously, but you should be familiar with this term. And where you're most likely to see index of refraction come into play first is in Snell's law. And so what Snell's law tells us is that the angle of refraction, if I define theta incident as the angle here, so if I define theta incident as this angle, and I define theta transmitted as this angle, these two angles are related by Snell's law, and we will talk about Snell's law in the next lecture. So that's a very important property. Um, At optical wavelengths, the permeability is almost always equal to mu naught. You have to actually specifically try to get magnetic behavior at optical wavelengths. And usually with optical instruments, optical phenomenology, we're not dealing with microscopic wavelength scale observations like we are at RF. Now, you can certainly make instruments that can manipulate materials or interact with materials at wavelength scale, but those are far more advanced than what we're talking about here. And so refraction, as we see here, was one of the first effects that was observed, and the index of refraction was used to describe it. We can define the index of refraction as the ratio between the phase velocity in free space to the phase velocity in the material. And for most materials, the wave slows down when it enters that material. Okay, so the speed of light in vacuum is larger than the speed of light in the material, so the index of refraction is typically greater than 1, and how much greater than 1 it is indicates how much slower the wave propagates in that material. For general materials, the index of refraction is given by this ratio, and for non-magnetic materials, it's the square root of epsilon naught, or epsilon over epsilon naught, or square root of epsilon sub r when we're dealing with non-magnetic materials. And we'll talk about Snell's law in the next lecture. The last concept that I'm going to introduce in today's lecture is group velocity, and we're going to talk about it very briefly. The phase velocity gives us the speed of propagation of a wave at one frequency. But a single frequency wave can't carry any information, because information would be a change in that wave. And if I have a pure sinusoid that has no bandwidth, it must exist for all times. It can never start, it can never stop. As soon as it starts or stops, it can carry information, but that starting or stopping gives it some amount of bandwidth. And so when we want to describe how information is transferred by a sinusoidal signal, we need to be talking about how a packet of wavelengths that could be very small but non-zero bandwidth propagates. So we're not going to derive this relationship. It's sort of straightforward. If you understand Fourier theory and you understand wave propagation, it's related to the Fourier transform and the Taylor series expansion of the frequency as a function of the wave number. Okay. But we define the group velocity as d omega d beta. Okay. So for plane waves, we have a relatively simple relationship between omega and beta. We say beta equals omega square root mu epsilon. Okay. So d omega equals beta over the square root of mu epsilon, and d omega d beta equals 1 over the square root of mu epsilon. So for propagation and plane wave propagation in lossless media, the group velocity is equal to the phase velocity. But in general, that's not the case. What I'm showing you here is the dispersion diagram, the relationship between omega and beta for a waveguide. We will derive this in lecture 10 or so, lecture 9 or 10, when we talk about propagation in rectangular waveguide. But this is what the relationship between omega and beta is. Right? Here is the actual dispersion relation, and this dotted line is the dispersion relationship for a plane wave propagating in this particular material. We see that as we decrease our frequency, we get some curvature to this. As we increase our frequency, this line asymptotes to that line. But as we decrease our frequency, we get curvature, and we actually end up with something called a cutoff frequency, and we'll talk about the physics of that a little bit later on. For any given point on this dispersion diagram, I can define the phase velocity as the slope of this line. It's omega over beta. Right? Omega is the rise, beta is the run, and that gives me the phase velocity. And I can define the group velocity. I can define the group velocity as the slope of the curve. So here I've got d omega, d beta. Okay? And so even in this instance where we see that the phase velocity is greater than the slope for a plane wave, so the phase velocity is greater than the speed of light, the group velocity is always less than the speed of light. You can play some tricks and you can get things called superluminal group velocities, but you have to be a little bit careful when you deal with that sort of thing. So that comes to the end of this lecture. The tutorial topics are around computation of phase velocity in materials, computation of group velocity in materials, and identification of some dispersive media. In this particular case, we're primarily going to be applying the formulas that we develop here or in your textbook to some specific material problems.